This is Talha Shafiq. Here we are to discuss about the modeling of electromagnetic navigation systems. Before starting, let's learn about the electromagnetic navigation system and its application. Now, I would like to introduce my group members who collaborated with me in this project. Myself, Talha Shafiq, a mechanical engineering student.
Now this is Mohammad Hassan Khalid and I am currently studying mechanical engineering from NAD University of Engineering and Technology.
Myself, Sayyid Muhammad Inzramuddin, and I am the student of Mechanical Engineering of NAD University of Engineering and Technology.
Magnetic navigation system is actually a technology to control biomedical devices inside the human body to perform minimal invasive surgery by means of magnetic field. As these magnetic fields can penetrate through biological tissues while being virtual harmless. But what are actually minimal invasive surgeries? Surgeries which is done with small incisions or cuts and few stitches instead of large openings of skin, usually done with robotic technology that allows the surgeon to control the device. Now let's talk about how magnetic navigation system works. Magnetic navigation systems can either be performed by set of moving or permanent magnets or by systems comprising of several electromagnets, which is known as electromagnetic navigation system. Magnetic navigation results from generating magnetic torques and forces on the navigated magnetic agent by modulating the magnetic fields. Here, this technology is also used in controlled wireless capsules for non-invasive examination of the large gastric cavity. Also, it is used in maps, and in this video you can see in the bronchoscopy steerable catheters being used, which are controlled by using magnetic field which is generated by electromagnets outside. Now let's talk about the modeling of magnetic navigation system. Modeling a magnetic navigation system consists of determining the magnetic field flux density at different locations within the workspace. Accurate modeling the magnetic fields of magnetic navigation system is important for precisely steering the tool and even more important for tracking devices in a magnetic navigation system due to significant position dependency of magnetic fields. While using electromagnets, the relationship applied between current and resultant magnetic fields is important. So, by the principle of superposition, assuming linear magnetization of the course on the magnetic fields, the magnetic field is given by the first expression. This equation does not hold for materials exhibiting saturation due to the increment of external magnetization fields. So, the relationship between current and magnetic field is no longer linear. Therefore, a more general expression is used to take account into these effects, which is in expression 2. This expression G can be determined by measuring discrete magnetic fields that span the entire space currents and then interpolating a smooth function between the field measurements, but this approach becomes inferior.
Now let's talk about interpolation of magnetic field. Magnetic field data as discrete data points that is either obtained from finite element modeling or by physical measurements by using magnetometer can be interpolated in space to obtain continuous function representation of the field. Interpolation is beneficial as it is completely independent when magnetic field data is available and it can yield accurate continuous representation of the field with less efforts for parametrization. These methods become intractable when electromagnet's effect cannot be separated due to nonlinear magnetization. The methods are structured grid methods and unstructured methods. Structured grid methods further include into tricubic 3D interpolation, tricubic Laplacian constrained scalar field interpolation, B-spline interpolation, Laplacian constrained 3D B-spline interpolation, and unstructured methods further include into scalar radial basis function, divergence-free radial basis function. We used synthetic data that was obtained from Electromagnetic Navigation System model to evaluate and compare the different proposed magnetic field interpolation methods. Because we were concerned with the interpolation of general field space magnetic field rather than accurately modeling the magnetic field generation of a particular EMNS model. We spanned dataset using a set of 100 randomly generated electromagnetic current vectors with workspace of cube size 20 cm and grid size 16. We used metrics such as root mean square error, normal mean root square error, mean absolute error to evaluate magnetic field prediction accuracy. The performance of an radial basis function interpolant depends on the value of its shape parameter due to the well-known uncertainty relation and the interpolation of performance. We evaluated the effect of the shape parameter on the mean normalized root mean square error across all components in data points using the previously prescribed data set.
अभी ये बंद हो गया, वो फुदूल की जा रही है.
कट तो हो जाएंगे. Now, let's see the comparison of field interpolation performance. In magnetic field, comparing the methods for RBF methods, shape parameter is used. Measurements are performed on the increasing grid size between 3 and 6. All methods are showing that by increasing grid size, there is a natural increase in performance. As we can see, the best overall performing methods for RBF, G3D and SPL3D, both in field and grid. Also, we observed that the divergence-free version of RBF were worse on comparison than their scalar counterparts, while for RBF, physically constrained methods performed worse. That was not the case with the tricubic method since tri-LPL consistently outperformed tri-3. In magnetic field gradient, the gradients are estimated from interpolated field values. The gradient is usually represented by the 3x3 gradient matrix. The best performing interpolants were again RBF, G3D and SPL3D.
Let me tell you about the methods we used in modeling of driven magnetic field. Number 1. Multipole electromagnet model. We trained a multipole electromagnet model of order 2 on a subset of previously mentioned training dataset, as it is usually considered of sufficient order to capture the field in the workspace of an electromagnetic navigation systems. Data was discarded if the maximum electromagnetic current exceeds 5 ampere in order to ensure that the electromagnets did not exhibit saturation and that linearity assumption was ensured. Number 2. Saturated multipole electromagnet model. A natural extension to linear magnetic models is to include a correction for the saturating electromagnets. We tested different sigmoid functions using least squares fitting to model the relationship between the magnetic field magnitude and the current on a single electromagnet. Number 3. The modeling of an electromagnetic navigation systems can be cast as a multivariate regression problem, which can be solved using nonlinear black box models. And number 4. Convolutional neural network. Accurate simulation of 3D fluid flows using deep fluids. By modeling a vector potential, it was also shown that divergence-free fields could be obtained. Now we discuss field prediction performance. To evaluate the prediction performance of the models, two general goodness of fit metrics were used to compare the measured and predicted magnetic field. These included the mean absolute error, normalized mean absolute error, the root square error, and the normalized root mean square error. Now we can see in table number 2 for different methods the predicted result for all the performance metrics. The mean absolute error for multiple electromagnet model is the highest, but it is the lowest for the convolutional neural network. Similarly, the normalized mean absolute error was highest for multiple electromagnetic model but lowest for convolutional neural network. Also, root mean square and normalized root mean square error was the highest for MPEM and the lowest for CNN. Whereas R square shows how well a model's prediction approximate the real data and its value closer to indicates a strong performance while low values indicate low performance. Here from the table, R square for CNN is closest to 1 as compared to the other model methods. With every method, as we can see that the performance matrix keeps on improving as compared to MPEM. This can be proved in figure number 5. The predicted results are mentioned in table number 2, while we evaluated the mean absolute error separately for each bin and reported results in. Lastly, accurate modeling of magnetic fields generated by magnetic navigation systems is a fundamental task for magnetic navigation systems in robotics. For electromagnetic navigation systems with several large electromagnets, as can be expected in clinical applications, the nonlinear magnetization of electromagnets and interactions between electromagnets render magnetic field prediction tasks challenging.